Hello and welcome. This is the final lecture for SFU Math 152 Calculus 2. My name's Brenda. So this is section 11.11. We are going to talk about just a couple of uses of the Taylor polynomial. So we had quite a long lecture last time on how to find the Taylor series for a function, and really for most of the functions that we're dealing with at this level, we'll always be able to find a Taylor series. So what we can do is take any function, find its Taylor series, and then we can truncate the Taylor series and effectively turn it into a polynomial. Polynomials are easy to evaluate, they're easy to differentiate, they're easy to integrate, and so we can use them for approximating the functions in a relatively straightforward manner. So this is a really high power tool for that, at least. There are other things as well, but that's definitely one of them. Okay, so just going to cover how to bound the error when we use these things, and a few other little things here, and that is going to be it for the course this semester. Okay, so what we have here is a reminder of what we saw last lecture. That is, if a function has a power series, and we're basically just going to assume that with the functions we're using, then there is how you represent the function as a power series, and you need to be able to compute those derivatives at some number a. That number is sometimes chosen to be 0, but that is where we center the power series at. Okay, that representation is called the Taylor series of the function f at a. Okay, and then we also had the Taylor's inequality. That is to allow us to bound the error by using the Taylor series if we take a certain n number of terms. We of course can't add up all infinite number of terms to get a value for a function with that representation, so we have to truncate at some point, and then as soon as we truncate, we want to know what is the error. The way we do that is we use Taylor's inequality, and we put a bound on the n plus first derivative, and we also observe that we're going to be using the approximation within a distance d from the place where the Taylor series is centered, and then under those conditions, it is the case that the error, the remainder, is bounded above by this expression here. So that allows us to nicely put on a bound. Okay, I want to just say a few things here before we go to our first example. Let us consider something. I just want to talk about the idea of where we center them. So, for example, if we have the function f of e to the x, like f of x equals e to the x, and we center it at x at a equals 0. Okay, so let's just draw a little graph of e to the x. It basically looks like this. If I center it at 0, it means that my 0th order approximation will be this, the constant. And then my first order approximation will be this, okay, a line. So this would be, well, let's just write out what e to the x is. I'll write that out. The Taylor series of e to the x at x equals 0. It looks like this. We've seen this already. It looks like this, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot, dot, dot. Okay, if I were to take the t0 approximation, that's going to be 1. That is this line right here. Okay. If I was to take the t, that is a constant. If I was going to take the t1 approximation, it would look like this, 1 plus x. That is right here, t1 of x. Okay, and the idea here I'm trying to make clear is, in this case, we are centered here at a equals 0. So all of our approximations are centered around that point. Okay, now if I was going to look at what t2 of x is, it is 1 plus x squared, oops, sorry, 1 plus x squared over 2 factorial, and that is a parabola centered here. So I'll just try to draw that in here. That's going to look something like this. Some sort of, it won't go up faster than the exponential. That's some sort of a parabola centered around there. Okay, so that this is the constant, and so that is what I would do if I wanted to use my approximation to e to the x near 0, because you can see that it is most accurate around 0. If I wanted to use my Taylor approximation somewhere else, like say I was very interested in what happens here at say 10, then I would center my Taylor series around 10, and I would have my T0 approximation here, my T1 approximation here, like that, because I would get less error if I used the Taylor series centered here at 0. When I was really interested in round numbers 10, I would need to have more terms to get the same accuracy. So I pick the place where I'm going to center my Taylor series, this thing right here, the x minus a. I choose that a based on a practical consideration. Where do I care about this? Do I care about e to the x close to 0? Do I care in my application about e to the x close to 100? Do I care about e to the x close to minus 50? Whatever that number is, I choose the powers of x to be close to where I want to use my approximation. That means I need less terms to get the same accuracy. And you can see that here because of this thing here. The remainder here depends on x minus a. So if x is close to a, then this will be small, and the error bound will be lower, which is of course what you want. Okay, so we're going to bear that in mind when we pick where to center. If we don't know at what value of x we're going to be wanting to use our approximation, then you might as well just pick 0, because it makes it easier to compute. Okay, so in this case, I've got here, say for example, the T2 approximation, the second degree Taylor polynomial to e to the x. And so then it is the case that R2 of x is T2 of x minus e to the x. And so the R2 of x, that is the error that I will be incurring, would be bounded by this thing here, the third derivative. Well, let us in fact do it this way. The absolute value of m over 3 factorial times x to the 3, where m is greater than or equal to the third derivative of e to the x, which is just e to the x. Okay, where on the interval in which I wish to use this thing. So you need an interval. You can't just specify the error for all possible values of x. You need to be specifying within this interval. If you use x within this interval to approximate e to the x, I can guarantee you an upper bound on the error. Okay, we're going to now see an example of how that works. I just want to try to make it clear why we are having changing this value of a. Okay, let's do this here. So here's a question. Approximate f of x equals x to the 2/3 by a Taylor polynomial with degree 3 at the number a equals 1. And why is that chosen there? Is because 1 is midway through the interval that you wish to use it. You're interested in what the value of f of x is for values of x between 0.8 and 1.2. And you're going to do this by using a Taylor polynomial. So you're going to center your Taylor polynomial midway through the range. That's going to get you the best error bound. Okay, so let's just find out what the degree 3 Taylor polynomial is for this function. I do what I've done several times before. Maybe stop the video and do this yourself and see if you get the same answer. So I'm going to take a look at the function and its derivatives. And I'm going to evaluate all of those at 1, because that's where I'm centering the Taylor polynomial. So I'm going to have the function itself, first, second, third derivative. So the function is x to the 2/3. The first derivative is 2/3 x to the minus 1/3. The second derivative is minus 2/9 x to the minus 4/3. The third derivative is 8/27 x to the minus 7/3. Then I evaluate all those things at when x is 1, and I get 1 2/3 minus 2/9 and 8/27. Now I can easily write out the T3 approximation, the polynomial that approximates x to the 2/3. It looks like this: 1 plus 2/3. Make that a bit neater so we can read it. X minus 1 minus 2/9 x minus 1 squared divided by 2 factorial plus 8 over 27 x minus 1 cubed over 3 factorial. That is a degree 3 polynomial that approximates x to the 2/3, and it is expanded around x equals 1, and that the reason for that is midpoint over the interval on the values of x that we are interested in. Okay, there it is. That's answer to part A. R3 of x then is less than or equal to m times x minus 1 to the 4 over 4 factorial, where m is a less than or equal to the fourth derivative of x. So then I immediately, oh shoot, I need another one of these things, so I'll go over there and calculate. I need the fourth derivative. This is going to be for the error bound, and I'm going to get here minus 56 over 81 x to the minus 10/3. Okay, so the fourth derivative, I just calculated that. The fourth derivative is minus 56 over 81 x to the minus 10/3. And I want to maximize this. I want to maximize on the interval where I want to use this T3 approximation to my function. And that interval is this guy here from 0.8 to 1.2. How do I do it? Well, I've got a function. Here's my function. I want to maximize it on a closed interval. So we use the closed interval method from Calculus 1. Okay, that means I'm going to have to take the derivative and look at what's happening with this function. So I take yet another derivative of this thing. So I take the fifth derivative, because what I'm actually doing is looking at the first derivative of this function I want to maximize, and the function I want to maximize happens to already be a fourth derivative, so I'm taking the fifth derivative, and I get this thing here, 56 over 81 times 10/3 x to the minus 13 over 3. So now I look at this and I see that this thing here is always positive, right? In the interval from 0.8 to 1.2, that thing is always positive. That means the derivative is always positive. Derivative is always positive. Therefore, the function is increasing. Okay, that's what a positive derivative means. If the derivative is positive throughout the whole interval, the function is increasing. So I'm not going to have to really employ the completely full interval method. So that means that the maximum is at the right endpoint. At x equals 1.2. Okay, so I can now calculate what m is. M is the maximum value that this function here can obtain, and that is m will be less than or equal to 56 over 81 multiplied by 1.2 to the minus 10/3. Okay, I've taken the absolute value. Okay, that then allows me to compute what R4 of x is. The maximum sized error for using this third degree polynomial for the approximation is going to be m. And then I'm looking at the next term here. I've figured out the biggest value for this, and then I want to also figure out what the biggest value for this thing here is. Okay, I have a lawn mowing situation happening outside here. Let me just shut the window. See if that helps. Sorry about that. I'm picking up a bit of noise from a lawnmower. Okay. All right. So we're trying to compute this thing here, R3 of x, and we have computed what m is, and then we are looking at what is the maximum value I can get here. So I want the distance between x and 1 in absolute value to be as big as possible. So that is going to be 0.2. So I'm thinking here of 1.2 minus 1. That's the biggest I could get with my interval. So remember, my x values have to be in this interval, 0.8 to 1.2. And I'm trying to think what is the biggest value I can get here, and that is the biggest value. And then I have to divide this thing by 4 factorial. So that is the error bound on using this approximation for x to the 2/3 in the interval between 0.8 and 1.2. Okay, be careful. Don't assume the maximum. Okay, it did happen this thing in this case. Don't assume a maximum at the endpoint. Okay, you need, and in this case it was true because the function was strictly increasing. So you can you recall these kind of things. You should look for strictly increasing, then it will be at the right endpoint. You could also see if it's strictly decreasing, then it will be at the left endpoint, or you might have you might have something like this where you need to find this point here. Okay, and you need to know where the critical point is. That's where the derivative is 0, and then so that whole closed interval method, you need to have that in your back pocket so that you can figure out what that value of m is. Okay, so now we could use our T3 polynomial here that we computed. This is what we're doing. We could use this to approximate this in this interval, and we'll guarantee you that the error between what we tell you the number is and what the actual number is will be no more than this. That's the idea. And we can convert pretty much any function that we're dealing with in this course into a polynomial, and then we can use the polynomial with some sort of error bound. This can make calculations much simpler, and the whole thing more amenable to dealing with this, in particular, complex functions. So here's one where it would be very difficult to do anything without making some sort of approximating function. So we want to approximate the area between this curve and the x-axis for x between minus pi and pi. So what does that? What this question is asking us is to take the function y here, which is sine x over x, and that function looks like this. Let's just try it this way. Like that. That's symmetric. Okay, that's best of my drawing, symmetric. Okay, it's asking us to compute this area from minus pi to pi. And we know how to do this actually. What we would do is say, okay, so what we're being told is we are being asked to find this integral, the integral from minus pi to pi of sine x over x dx. Okay. I mean, already we have tactics for this from earlier in the course, so you could remind yourself of those. We could use the trapezoid rule. We could use the midpoint rule. We could use Simpson's rule. Look at that. Look at me. We already have like a variety of different tactics. We're not going to use any of those methods here. I just want to remind you of those. What we're going to do is say, okay, we cannot actually integrate this. This is a function that does not integrate in terms of elementary functions. And in fact, we have a special notation for this function. And so this is a bit of an aside, or just maybe something for you to get excited about. And that is we have, so we name this function, that is this thing here. Okay, and we label it this way. Okay, this of course is a definite integral, so this is a number, and it is some number. We're going to try to figure out what that number is. So our idea of what to do here, different from what we used to do before, is to take this right here, and replace with the Taylor series. And then that will be a polynomial. Then we could easily integrate and give you a number. And then we also want to bound the error. So we can tell you by how much are we out. Okay, so an extension for those of you who wish to think about this extension, I want you to think about the connection between using the Taylor series here and the numeric methods we have listed above, enumerated above, and the numeric methods above. Okay, the numeric methods we listed here above: the trapezoid rule, midpoint, Simpson's rule. Just think about what's happening and see if you can see a connection between me taking this integrand, replacing it with the Taylor series, and then integrating in that manner. Okay, so that's my idea of what to do. Replace the integrand with the Taylor series. So now I need to find the Taylor series for this function. And how am I going to do that? Well, I could do that by using the quotient rule and taking a zillion derivatives, but boy, that is painful. And so what I'd way prefer to do is recall that we already have seen the Taylor series for the sine function. It's an odd function. It has the odd powers of x. So we know the Taylor series for the sine function. And then we can simply divide both sides by x, and we get this function here, 1 minus x squared over 3 factorial plus x to the 5 over, x to the 4 over 5 factorial minus x to the 6 over 7 factorial. It's amazing how much harder it is to write the different number. X, like put an 8 here and a 9 here. Okay, like that. Okay, so now I mean, this is an odd function. We know that sine's an odd function. And you notice what's happened. Now we see only even powers here. So we know that this is an even function. And you can see that from the graph I've drawn. It's an even function. Okay, so we've got the power series centered about 0. Why did I center it about 0? This Taylor series right here is centered about 0. Okay, that's because I'm interested in the interval. The interval I'm using this thing on is minus pi to pi, right? I'm wanting to integrate from minus pi to pi, so I'm using my function between minus pi and pi. 0 is right in the middle of that interval, so I'm going to center my Taylor series about a equals 0. And when I wrote this one for the sine function out of my head, that one is the one that we found centered about 0. Okay, so now I have a choice. I'm going to take my integral, this guy, and I am going to now turn it into an approximation. I know this comes out to some number, and as soon as I do this step, it's going to turn from an equality into an approximation. And I'm going to use the T2 polynomial. Sorry, pause here. I was just thinking about something. Okay, I'm going to use a T2 polynomial. So that means I'm going to truncate right here. Right here. Okay. I can get more accuracy if I chose to use the T4 polynomial, but I'm just going to go here for the T2 polynomial. So I'm going to approximate my integrand, this guy right here, with its T2 polynomial, which is going to look like this: 1 minus x squared over 3 factorial dx. And now look, I've turned something that I cannot integrate into something that I can integrate. That makes me really happy because then I can get an approximate number out. So I'm going to see what this is equal to. I will integrate. I get x minus 1/18 x cubed evaluated at minus pi and pi. And when I make that calculation, that comes out to 2.83. Okay, so let's just, so this is with T2 of x. Okay, then I could, if I wanted, of course, I could instead make a T3 approximation. So I could say, well, this integral instead is actually approximately this, and this will be better. Okay, I'm using more terms. It's going to be better. I could use the T2, a T4 polynomial. Let's just write that as 5 factorial. Okay, so and I go ahead and integrate this and get a number. It's a polynomial, and I get this number. And this is with T4 of x. Okay, so you could keep doing this till you get to the desired degree of accuracy. And just to, I check this to get a more accurate answer faster, just to sort of see how we're at. I checked with Wolfram Alpha, and Wolfram Alpha gave me the answer. Answer is 3.703. So it's not too bad. We're by the time we've got to a T4 polynomial, we've already got we're already within that first decimal place. I tried with the T6 polynomial, and that one gave me the answer I got there was check this yourself and see. The answer I got there was 3.6868. So I'm getting closer. So the point is I can get closer and closer and closer to what the answer is by using more and more terms in my Taylor series. So this is a way that we can take a function, find its power series, find its Taylor series, and then use some number of terms, a finite number of terms of that Taylor series in order to vastly simplify our calculations. And then when we do that, we incur an error, and we also are able to bound that error and tell you, well, we're within this amount. And if that's good enough for your application, all is well. Okay, folks, that is the last lecture for Math 152. This topic coming at the end, really important topic. Really spend some time on this. It's a very important idea. And I will, for the people who are in my class at SFU each semester, I will be giving Zoom lectures or in-person lectures as the semester goes along about doing extra problems, midterm review, final exam review, all that kind of stuff. But this YouTube channel is containing a complete set of the lecture notes that covers the course material at this point. Thanks a lot, and I hope that you find this material as interesting as I do. Bye.